Hello everyone. Let's again solve one more problem that is quite interesting and quite conceptual actually. So you can read this question, and this is actually from again Parker Smith Problems in Electrical Engineering Volume 2. I picked up example 30.38 problem from there. So this is actually uh, combining your knowledge of three-phase transformers with that of the voltage drop regulation and all these things. So read the question, try to understand the question, and try to attempt the solution. I'm not saying try to solve it. I'm trying to saying at least attempt the solution. And once you made your attempt, and then you kind of understood some what is the issues with this question, then you can look at my answer, and hopefully you will learn something from that. So pause the video now. If you don't have this habit of pausing the video and looking at my videos, just having the question and answer continuously, at least develop that habit now. Pause the video, understand the question, and then we'll see. Try to attempt it and we'll see. Okay, I'm now jumping to the answer. So this kind of things, it's good to draw a diagram. So let me draw the diagram. So the primary side is delta connected. So the line voltage between this supply, so this is supplied from a three-phase source, and the line voltage is 6000 volts. So a three-phase delta star, so this is delta, and let me draw the star also. Let me show the core in between, and then let me draw the star side. So this is the star side of the supply. Now there will be equivalent resistances and all these things. So this is resistance, reactance, and again this is resistance and reactance. So this is R naught 2 plus JX naught 2. Same for all. So when I say R naught 2, the primary side resistance already has been transformed to the secondary side and incorporated into it. So that is why I don't have to show that here. So the terminal voltage V2 will be here. And what will be the line voltage here? This will be the line voltage E2. And what will be the phase voltage? So the phase voltage will be E2 phase. So this is induced EMF line. So this is induced EMF, actual induced EMF in each phase, E2. So you know the relation between these two will be one factor of square root of 3. So E2 into root 3 will be E2 of line to line voltage. Now there is a transformation ratio. So this winding and this winding, let's say, are paired, or let's say these two windings are paired, for example. That means they are wound on the same limb, and these two are paired, and these two are paired. So that is how a three-phase transformer is there, where the one-to-one pairing of phases of the secondary and primary will happen, and the turns ratio will be at this point. So here there will be a turns ratio. Now here E1 will be there, which is exactly equal to V1. So V1 equal to E1, because there is no voltage drop here, because the resistance and reactance have already been transferred to the secondary and considered here. That is what is given in the question. Alright, so I can also write the percentages. So what is given here? The terminal line voltage on the star delta is observed to be 450. Okay, so here this is 415, terminal line voltage. When the load having power factor of 0.8 lag is being supplied, the equivalent resistance and reactance drops are 1% and 5% drops. Find the turns ratio of the transformer. So to find the turns ratio of the transformer, I already know. So what is the turns ratio? turns ratio here is nothing but E1 phase divided by E2 phase. So E1 phase I already know. So now the job is to find this E2 phase. So for that, I have to find the drop here. So what is the drop? So Vx and Rx are given. So therefore, I can find the drop. Now you can see what about the drop here? So this is also 1% and 5%. So to avoid confusion, actually what happens is these are per phase values. So 1%, 5% in each phase it will be dropping. So first what I'll do is I'll write down the formula for voltage drop. See, this is under full load. Okay, the question is asked under full load, what it is. So the voltage drop is nothing but Vx cos phi x cos phi 2 plus, sorry, this is Vr, Vx sin phi 2. So Vr and Vx values are given 1%. These are actually per phase voltages. So that is nothing but 1% into 0.8 plus 5% into 0.6. So this is 0.8, 5 into 6 is 30, so 3.6%. So this is 0.8%, this is 4.4% is the voltage drop. Now this 4.4% of what? So the line voltage is 415. So V2 line voltage is 415. So V2 phase voltage will be 415 by root 3. So that will be how much? By the way, let me just verify this. Okay, so 415 by square root of 3. So let me do that. 415 by square root of 3. 239.6. Now from this I have to reduce this. So this 239.6 corresponds to the voltage which is after dropping 4.4. So what is E2 phase? That is something which is correspond to 100%. So how do I calculate? So this after dropping of 4.4, so remaining voltage is this one. So 100% minus is corresponds to 100%, whereas 100 minus 4.4 corresponds to your V2 per phase. So therefore, if I just multiply, so E2 per phase will be 239.6 into 100 divided by 100 minus 4.4. So how much will that be? 239.6 into 100 divided by 100 minus 4.4. So I'm getting 250.63. So I'll approximate to 250. I'll not approximate 250.63 volts. So this is the E2 per phase. Now what is the on the other side? What I have 6,000. So now I can find the turns ratio. So turns ratio is nothing but 6,000 divided by 250.63. So let's do that. So 29 point, so if I just ignore this, it is 24. So let's round it to 250. So it is 24 turns ratio. So therefore the final, if I want to write it in the form of ratio, it is 24:1. So this is your final answer. So I hope by drawing this kind of diagram, by understanding, analyzing which value goes where and all, you are able to get more conceptual understanding of transformer. So this is a three-phase transformer. So I hope in this entire set of video, in this lecture 7, if I want to summarize lecture 7, so neglect I naught. By neglecting I naught, we simplify vector diagram. After simplifying vector diagram, transfer primary voltage drops that are I1 R0, I1 R1 and I1 X1. These primary voltage drops to secondary. Then from that we obtain simplified vector diagram. So the simplified vector diagram was something like this: V2, and this is I2 R02, this is I2 X2, and then this was V1. So this simplified vector diagram we got, and from this again we just do this particular trick, and then we got the obtained voltage drop, approximate voltage drop. So approximate voltage drop we got was nothing but I2 R0 2 cos of phi 2 plus I2 X0 2 sine of phi 2. But then this formula applies only when the lagging load is there. For leading load is a minus 1. So once I got this, then if I divide, so voltage drop divided by voltage at no load is nothing but this, everything I divide, then I get VR cos phi 2 plus or minus Vx sine phi 2, and this I'm calling it as a voltage regulation. So and then we did some problems with three phase and all this thing. So this is just a quick summary of lecture 7. I hope you learned something from this lecture. We'll see more in future lectures. Thank you. If you like this video, please press the like button, and I'll be making a series of videos on electrical engineering. So please do subscribe. I have already made a lot of other videos also in electrical engineering. So subscribe to my channel. Thank you.